Hi friends, welcome to the channel Digital Design Academics to Industry. Today we are going to understand how we can solve the problems in setup violations. This is session number 3. To understand this session, you have to go back for session 2 and session 1. So let us start. In session 2, we discussed how setup and hold violations comes in the design. So this is a presentation number 1, presentation page number 1, which tells about the relation of analog behavior with the digital behavior and how the metastability comes with the setup issues. So this is one example of setup violation. One first example of setup violation is this: when data is being launched here and data is going inside the setup window, as we have discussed in previous sessions. By concept, data launched here should reach here maximum. It should not go beyond this window. So let us take an example. If this is a 10ns, this is 10ns, and T setup is 2ns. Let us say T setup is 2ns. Means data should arrive here before 8. It means TCQ plus T combo plus T wire should be less than 8. TCQ, T combo plus T wire should be less than 8 to make this setup violation. But it is going beyond 8. So it is something coming like here 9. We are facing one NS issue here. We are facing one NS issue here. So let us see how can we resolve this kind of issues, right? So we were saying that TCQ plus T combo plus T wire should be less than 8. So initially, let us say initial failing path was like this. This was a failing launch cap edge, capture flop, and data was flowing like this timing arc A. Here, so let us assume that TCQ is 2ns. These are mainly in picoseconds, but we are assuming to make clarity, right? TCQ is 2ns and T wire is again 3ns, let us say, question delay or the wire delay, right? 5ns. We can say TCQ also 3ns to make the example good. TCQ is 3ns, T wire is 3ns plus T combo. T combo is coming like 3ns here, which should be less than 8. Now, as a digital designer, we have to understand which part of the design to be touched, right? So I have explained in sessions 2 how TCQ comes. TCQ is a parameter of library, synthesis library, or the fabrication characteristics of a flop. This is a part which is coming from the PD, physical design. Like for example, how we are placing the flops. For example, I am placing here or I am placing very far away, congestion and what are the routing distance and these things, right? So this is a PD dependent. As a RTL designer, what we can do? I am an RTL designer. T wire is coming from a PD. PD says I will take 3 nanoseconds, sure. Synthesis team will say that I am going to take 3 nanoseconds, sure. But how to resolve it? I will say I have to resolve this, reduce this 3ns. So what I will do, between this flop, for example, and there is one more flop, this TCQ was 3ns, this combo was 3ns, and this total was 3ns. So what I did, I broke this in between. So 1.5 for any number of combo, we have to divide it, right? It depends upon the logic how it can be partitioned. It is not exactly half, but for example, I am doing it. It is possible that 2 is going there, 1 is coming there. So let us say we partition it. So what we did here, we put a flop here. And this logic, 3ns, we put one stage of the AND gates here, whose one input is coming from this flop and another input is coming from different flop, right? And then ORing and inverting is happening here after this. So another timing arc is going like this, and one timing arc is going like this. So now if the TCQ is 3ns, wire delay is 3ns. I don't know how they will route. We will keep it 3ns. It is 1.5. 6 plus 1.5 is equal to 7.5. So if you will see back, data is launched here and it is reaching to 7.5. There is no setup violation. So RTL designer is able to fix this problem, where TCQ was a problem of the synthesis library or the fabrication characteristics of the gates. Wire was the PD, how it is getting placed. So TCOM is under the control of RTL engineer. So we have to look in that way. And this bifurcation of the logic is very critical. We will see these things in miscellaneous sessions where I will explain about the interview questions, specific interview questions asked, how to break these things, how to break the FSM states. We will discuss about these things in specific sessions of this, only for interview questions we can say that. Next part is, so we can't do, okay, so what is the next condition is this. Okay, let me erase all everything. Okay, so now a second problem comes. Second problem is this, that we have written the RTL and given our design to synthesis team. Synthesis team. This is the ASIC flow, right? RTL, do the lint check and everything, CDC checks and everything, give to the synthesis team. Synthesis team, they did the run the STA also. And when we run, they gave run STA, they found the timing violations here, like here, 0.5 negative here, right? 0.8 was reaching at 8.5 instead of 8. So they found a violation, timing violation, synthesis team. So they have choice. So they will send back to the RTL team and RTL will do this solution, bifurcating of this logic. But it will create a loopbacks, right? Means you are sending somewhere and it will take 2-3 days or 4 days, 5 days, like depending upon the teams, like how we do the checks. We have to run a lot of checks before submitting the RTL, right? And it will take run of 3 days something. So it takes 0 days, 3 days, 5 days, 11 days, whatever it is, right? So STA team say that we do something at our level. So what they can do? So every time when we have a synthesis library or a fabrication libraries, we have a high speed library and low speed library, right? Then we can choose the high speed libraries. Like W/L ratio was 3 earlier and it become 1 ns. Like for example, for a combinational gate, if W/L ratio was 3, then the delay was 1 ns, right? The drain current was less. When W/L ratio become high, delay become less and drain current become high. That's how we can reduce the T combinational delays. So this 3 ns will become 1.5 ns, something like that. And when it will become 1.5 ns, our timing will be meeting without doing this, right? But what is the loss here? The loss is that when we are going for higher W/L ratios, IDD current will increase and it will create a high power loss. So we will discuss it about the power loss when I will discuss about the low power designs. So you have to think about, this is a huge question. You have to think how we can do something to remove the setup violation with help of a voltage or VDD. The next question is that we were getting a timing violations here, right? It was reaching at 8.5. But if we move this direction, when we will move it to this direction, right? By 1 ns, it will come to 7.5. We will put a buffer of 1 ns and our problem is resolved. So this is another solution of buffer, putting a buffer. So this when we put the buffer here, setup violations can be get rid of, right? So for example, data are reached here at 8.5. We moved the capture clock itself, right? So it was like, so let us erase it, right? This is at 8. So this is a 10. So this is setup 8. Now we moved it by 1. So it become 11. And minus 2, 9 setup time. So data was arriving at 8.5. no metastability, no setup violation. So this is a third technique of resolving the setup violations, right? So we will discuss about the hold violation solutions in next session. Thank you everyone. Please like and subscribe, and please press the bell icon so that you can get the notifications of the next videos. Thank you very much.